Fieldwork number 6, Trigonometric Leveling. Trigonometric leveling involves measuring a vertical angle from a known distance with a theodolite and computing the elevation of the point. With this method, vertical measurements can be made. At the same time, horizontal angles are measured for triangulation.
Materials: theodolite, measuring tape, markers, range pole, plumb bob, and leveling rod.
The objectives of this fieldwork are to acquire and develop the skills of determining the vertical distance, elevation, and height of a remote point by applying trigonometric and related analysis, and also to develop the skills of reading vertical angles using theodolite or total station.
Procedures: consider this as the location assigned. Set up the theodolite at a convenient location and call it point A. Using the telescope, take sight at the topmost remote point. Read the vertical angle and record as A on Table 5, Trigonometric Leveling. Take another sight for the second trial to determine the instrument's precision.
Calculate the mean of the two vertical angles, or the angle of elevation, not the zenith angle, of the specified point from the first station. Set the leveling staff or rod vertically near the base of the remote point and take the level foresight on the rod to determine the height of the instrument. Transfer the instrument level, theodolite, towards the location of the remote point and designate it as Station B. Then measure its distance by taping from its initial position or Station A. Record this as distance AB. After centering the bubble of the instrument level, sight at the same topmost remote point sighted before, twice using the telescope, and record as beta on Table 5 Trigonometric Leveling. After recording these two observations of vertical angle, calculate the mean. Level the telescope while at B and get the height of the instrument by sighting the same leveling rod near the base of the remote point. Analyze. See figure below. The right triangles formed to determine the height of the remote point. This fieldwork will not consider the effects of combined correction of Earth's curvature and refraction.
Analysis of the figure.
For the analysis of the figure above, first, to determine the difference in elevation between the two instrument setups, we will have the equation difference in height of the instrument is equal to h1 minus h2. Consider the triangle B prime EF, then solve for the distance x using the tangent function. Tangent beta is equal to h1 minus h2 all over the missing x. Then, to determine the sum of distance AB and distance x for the analysis of the oblique triangle A'FD, we'll have the equation A'F is equal to AB plus x.
Consider triangle A'(FD) and use sine law to determine the distance FD. You can use the given equation below in order to determine the distance FD, where AB plus x over sine beta minus alpha is equal to FD all over sine alpha. Consider triangle FDG and determine the height of the remote point DG. We can use the given equation below in order to determine the remote point DG, where sine beta is equal to h minus h1 all over FD. Recording the data gathered. Here, we can record the gathered data to Table 4, double-random differential leveling, where we can input angle of elevation, mean vertical angle, height of instrument, mean height of instrument for stations A and B, trial 1, trial 2 for both stations. We can also record the measured distance AB and the calculated height of remote point.